First of all, a very good morning. A very good morning to all of you. So, in yesterday's session, we had started with the simple two variable model, and we will carry on with that. And much of the first half of my lecture today will focus on interpreting results in the two variable regression model. So as you can see, I have put it in red. The main talking points for today's lectures have been colored in red. Now, once I'm done with interpreting results, which is going to take a bit of time because there are several issues intertwined, we will go on to talk about models that can capture nonlinear relations between y and x in the two variable framework. So we talk about some models with that can capture nonlinearities, staying with one explanatory variable. Okay, and then we'll proceed to talk about the multiple linear regression model in terms of its assumptions, interpretation of results, and hypothesis tests. So that's the plan for the half day today till 1:30. Okay. So as I said, the first thing that I'm going to talk about is interpreting results in the two variable model. So if you can see on your screen, I've listed all the results that we are going to be talking about. Now here, just let me say one thing. When I say results, I'm talking about what you're going to see on your screen whenever you are sorry. So I'm going to talk about what you see on your screen whenever you have run a model, whenever you have estimated a model using any software. So the software could be Stata, the software could be Excel, any software. Okay, so that's what I mean by sorry. So yeah, that's what I mean by interpreting results. Okay. Now here are some of the things that we have already discussed, and these are in green. Okay. And I'm actually going to begin from there. Just take you through some of the ideas related to the coefficients, the predicted values, the residuals, which we had discussed yesterday. And then all of these in red are what we are going to go on to discuss. Okay. So we'll start with the concept of the R square of a regression, which is always reported as part of your output. And then we are going to have to revise some basics regarding random variables, because you see our OLS estimators are random variables. So they have means, they have variances, and the properties of the OLS estimators, which I will go on to discuss, are stated in terms of these means and variances of the estimators, right? So we'll have to understand some of those. And once we've understood those, we can talk about the concept of the error variance and the standard error of the regression. So these are also reported as part of the standard results when you see them. So I'll just show it to you. Now, once you know what is the standard error of the regression, you will understand what is the standard error of your estimators. So that's going to be the next thing that we talk about. And why is it important to understand all of these things? So as you can see, understanding is a big part of what we are going to do. It's very important to understand these things, because without that, you cannot really appreciate what is the statistical significance of the variables. And this is closely linked to the idea of conducting a hypothesis test. So we will talk about hypothesis tests, how to do those using t-statistics, how to do those using p-values, and also talk about the meaning of confidence intervals. So do you see that's a whole list, right? And all of that can be put in this box of interpreting results in the two variable model. Now, one good news for you is once you work your way through this long list, you see multiple regression will be a cakewalk, because whatever works in a two variable model simply rolls over to the multiple regression case, right? So once you've done these in detail, we don't need to really go through this again when we are moving on to the multiple regression model. Okay, all right. So with this, I'm now going to take you back to the results. So let me just show you what results I'm talking about. So this is exactly what we were discussing yesterday, right? To help you remember what this was all about, we started with some data. We started with some data on wages and on education. So the two columns I've highlighted in blue include wage, which is our dependent variable. Okay, so I'm just going to write that. So wage is my dependent variable and education is my explanatory variable. So you see, throughout this session, I'm going to call y. Whenever I say y, it's a dependent variable, and x, x1, x2, x3, these are going to be the terminologies we use for our explanatory variables, right? So this was the data. And again, for a quick recall, we ran a regression using Excel. How did we do that? We went to data. From data, we picked data analysis, which opened this dialog box. And in that dialog box, we chose regression, which opened another dialog box. And then we specified the range of the dependent variable, the explanatory variable. We asked for variable labels. We asked for residual plots, we asked for line fit plots, and we got all of those things, right? So here are the results that, that I got yesterday. Okay, so as this session is going to be all about interpreting results, let's start with what the results are actually showing us. Now, there are several things here which have been highlighted in yellow. Let's start with those yellow highlights. So I will remove this. I don't want to highlight this right away. Okay, so right. So now you can see there are only two things which are highlighted in yellow on your screen. One is alpha hat and the other is beta hat. Okay. So what is alpha hat? Alpha hat, remember, is the estimate. Okay. So alpha hat is the estimate of your constant term. So I'm going to put this in blue. All right. So remember what the least squares model does. The least squares model takes a scatter, right? So here you can see, so you can see the scatter right here, okay? So look at what the axes are showing, okay? So look at what the axes are showing. You have on the x-axis, okay, sorry. So on the x-axis, you are measuring education, okay? You're measuring the x variable. And on the y-axis, you're measuring wage, you're measuring the dependent variable. So what you have is in blue, okay? So this is showing the scatter plot. Why is it going up in straight lines? Can you guess? It's because of the way my explanatory variable is. My explanatory variable is a discrete variable. It is years of education. So years of education goes from 0 to 5, 10, 15. And for each year of education, you can see that here are the wages. Here are the wages, right? So for each year of education, you don't see only one wage. You see a whole scatter of wages, because even people who have, let's say, something like 20 years, let's say 15 years of education. Okay, so people with 15 years of education, you have so many incomes available. So those with 15 years of education can either earn very little income, or they can actually earn quite high levels of income, right? So that's your scatter. And as we learned yesterday, the method of least squares, what it does is it fits a straight line, right? So this is the straight line that has been fit using the method of least squares, right? So this is this is a straight line, okay? Yeah, so there you go. That's my straight line. Now, let's come back to my alpha hat. So what is alpha hat? Alpha hat is the intercept of this line. Now you can see this line is cutting the y-axis below 0, which is reflected in the fact that the intercept has a negative sign. Now, do I worry about that? I don't really worry about that because I don't care much about the intercept. The intercept is telling me what's the wage of someone with 0 years of education, right? That's possibly a data entry error or something like that. So intercepts, they should be kept in your model. So I'll tell you why intercepts are very important to be had in your model. Don't throw intercepts. But regarding their interpretation, mostly they don't have very, very interesting interpretations. Okay, so don't worry about the interpretation. Note that the intercept is negative in this case, which is showing in the line cutting the y-axis just below 0. And what about the slope? So the slope is, of course, so if I were to draw it here, so the slope is theta, right? And theta is equal to this, okay? So theta it's better to call it beta hat. So beta hat is equal to 0.54, right? Now, how did we get this beta hat? Okay, before I come to interpreting the beta hat, let me just remind you. So quickly, what are we doing? We are learning how to interpret results, and before we go on, we are just kind of doing a quick recap. Okay, so what is my beta hat? Here you go, sorry. Right, so my beta hat is calculated using this particular formula. And where did I get this particular formula from? Remember, I got this from the method of least squares. So what was the method of least squares all about? Very quickly, the method of least squares is all about fitting a straight line of the form y is equal to a plus bx to a given scatter of observations. Now, how do you fit that straight line? Again, recall, you fit it by minimizing distances on the line from actual distances, right? And what do you do? So basically, this is nothing but this plus, so yi minus a plus bxi, right? And once you open the brackets, right, that becomes yi minus a minus bxi, and you square those distances. You square them, and then what you do is you also minimize, right? You minimize these squared distances, and that is how you get. So the process of minimization involves, as you will recall, setting the partial derivatives to 0, and then you are getting these two so this is the intercept and this is the slope of your line of best fit, and that is exactly what is being used as alpha hat. So this is your alpha hat, right? And this is your beta hat, right? So once you have data on y, once you have data on x, which I have, right? So my y is wage, my x is education. So once you have all of that data and then you apply these formulae, what you get is an estimate of alpha hat and beta hat, where these, okay, so these formulae are the estimators, okay. So I think that's the amount that I want you to sort of recall at this stage, that using uh, this estimator. Remember, estimator is a formula, it's an equation. Using this estimator, I get beta hat and I get alpha hat when I have some data. And here on your Excel, on your screen, on the Excel screen, is that alpha hat and the beta hat. So the beta hat is going to be just highlighted in red. Sorry, so the beta hat is going to be red, okay, and the alpha hat is already in blue. So all of this we have done. That's the first thing, right? We get the coefficients, we look at their magnitudes. So right now I'm not going to say much about the magnitude except interpreting it. So what does this 0.54 mean? It means that for 1 extra year of education, hourly wage will increase by about 54 cents. That's it. Okay, right. Now, what else did we talk about? We talked about using alpha hat and beta hat to generate predicted values and to generate residuals. Now, what I have done is I have copied these predicted values and residuals from this part of the sheet to the original data sheet. So here are the predictions and here are the residuals. Now this is alpha hat in yellow, this is beta hat also in yellow. Now look what I have done. I have generated the predictions using alpha hat and beta hat. Now what are predictions? Predictions are nothing but what your model is telling you should be the wage of someone who has a certain number of years of education. Let's take the first observation. So, according to the data, a person who has 11 years of education, his wage is $3.1 hourly wage, right? Now, what is the predicted wage? The predicted wage is $5. How did I get the predicted wage? Very easy. To get the predicted wage, I just did, so what I did is the following. So you can look at the formula. I just did alpha hat plus beta hat into 11 and I got the prediction. Is that clear? Okay. And I just repeated this exercise for all the variables that you can see. So let me take the 12th observation. Okay. In the 12th observation, you can see a person who has 16 years of education, right, is actually earning $6. What is my prediction from the model using the values of alpha hat and beta hat? So alpha hat plus beta hat into 16 gives me more than $7.50. So according to my model, this person should be earning more. Okay. So this is a very simple exercise and I think you should do it to clarify your ideas when you're practicing. Okay. Check that the predictions that you are getting from your model using alpha hat and beta hat are exactly the same as what Excel is reporting. So please look at column C and column K. So if I remove all these annotations, you'll see that column K and column C, right? They're exactly the same. These are, so column C, which I've highlighted, is what Excel has reported. Column K is what I have calculated using alpha hat and beta hat. Now, the idea is that when I'm talking about model predictions, you should know exactly what is going on. Model predictions are the values that the model is saying you should get of the dependent variable depending on the calculated estimated regression coefficients. Okay, now let us look at the idea of residuals, model residuals. Again, something which we discussed in our previous session yesterday. So remember, our model is y is equal to alpha plus beta x plus u. Where the U are the errors are not observed. They are unobservable random variables. Now, when I have data, so when I have data on Y and when I have data on X, and I've used it to estimate alpha hat and beta hat, right? I'm actually able to also get an estimate for the errors, which are my residuals. So keep these ideas clear and correct. So errors, disturbances are always terms that are used to denote what you cannot see. They are important part of your theoretical OLS model. They are unobservable. All right. And residuals. Residuals are not to be mixed up with errors at all. They are distinct, they are different. So residuals are what you obtain once you have estimated your model. So once you have estimated your model, what do you have? You have Y and you have predictions. So instead of predictions, I'm just going to call this Y hat, right? So what is Y hat? Y hat is nothing but the predicted values. Just like this is alpha hat, this is beta hat, these are the estimates. Similarly, Y hat are the estimated or the predicted wages that you get out of your model. Is this clear? Okay. Now, so what are the residuals? So the residuals are nothing but Y minus Y hat. Okay. To see that clearly, see. Let's look at the first observation again. Now, in the first observation, I have someone who has 11 years of education. Actually, this person is earning $3.1. That's the data. But my model is predicting that he should be earning more. So Y minus Y hat is negative. I get a negative residual. Let's look at person number. Let's look at the fourth observation. Okay, so this one is the fourth observation. This is pertaining to someone who has 8 years of education. Actually, this person is earning $6. But then what does my model predict? My model predict that he should be earning much less, $3.4. So my model predicts that, look, someone who has fewer number of years of education, okay? Someone who has 8 years of education should be earning less than someone who has 11 years of education. And my model is fine. So 11 years of education, my model predicts you should be earning $5. 8 years of education, my model predicts you should be earning about $3. But actually, this person is earning $6. So in this case, Y minus Y hat is positive, right? So I get a positive residual. Also note that my residuals, which are in column M over here, okay, are exactly the same as the residuals that Excel has generated. So column F, I have just copied the residuals that have been generated by Excel. They're exactly the same. Again, let me repeat, it is very important that you take some data. Doesn't matter what kind of data in terms of size, some small data set, and you should do this exercise. Make sure that you are able to run a regression in Excel. You are able to generate predicted values and residuals using Excel. And then you should check that the residuals and the predictions are exactly following, how theory says it should go. Okay, so that's so far as the revision is concerned. That's so far as what we had covered yesterday and what I quickly wanted to run through. Now let's talk about another important result which is reported whenever you run a regression, and that pertains to what is called an R squared. Okay, so if you look at the results, you will see that right on top, okay, there is this particular uh, statistics which is getting reported, which is called the R squared of your model. So what is this R squared? You see, to understand what the R squared is, let me go back to what is it that we are trying to do when we are running a regression model. We are basically trying to understand to what extent the variation in wages can be explained by variation in years of education. To what extent people earn different wages, and not everyone is earning the same wage. They are all earning different wages because they all have different levels of education. That is what we are trying to do through this particular exercise of simple linear regression, when I'm regressing wage on education. Correct? Okay. So what is the answer? You see, the answer has broadly three parts to it. So what is the question? The question is, whenever I'm running a regression, what is it that I'm doing? I'm asking, to what extent is it the case that my the variation in my dependent variable is actually explained by variation in my explanatory variable? In this case, to what extent is it true that wages vary because people have different levels of education? Right? That is the exercise and that is the question. As I said, the answer has parts to it. The answer is not easy. So what are the parts? Let me indicate the three parts. So the answer to this question, first of all, lies over here. So it lies in the magnitude of your estimated coefficients. That's the, if you like, the first part of this answer. How well am I doing? The second part lies over here, okay, in circle number 2. What is the statistical significance of your variables? I haven't spoken about this yet, but I will do so shortly. And what is the third part? The third part lies over here. What is the goodness of fit? Or what is the R squared from my model? Right? So this is point number 3. Now we have already looked at 1. Now let us look at 3. We will come back to 2. Okay? So let us understand what the R squared is telling us. You see, the R squared is actually telling us something very simple. It is just telling us, so how much of the variation in y is explained by the variation in y hat? Bas, that's what it is telling us, right? So what is y? Y is wages in this case, and the total variation in y is basically the variance of y. You can just think of it as the total variance of y. All right. Now come to your model. So what is y again? Y is actual wages, right? Now, what is your model giving you? Your model is giving you predicted wages. So your model is telling you, we just talked about predictions, right? So your model is telling you, if a person has so many years of education as they have in the data, what is the wage that lies on the line? So if you like, let's look at what the model is telling us. I will just use this diagram over here. Okay. So this is what my model is actually telling me. Right. So let's take someone with let's say 15 years of education, right? So as you can see, people with 15 years of education, actual data tells me that their incomes can vary from here to here. But my model is telling me that on average, right? Remember, the model is all about the expected value of y. On average, such a person is going to earn some income like this, right? So this particular point, which I've circled in red, all right, and this whole thing is nothing but your y hat, right? So all these points are representing y hat. So you take any x, right? This is, so sorry. You take any x, let's say 10, this is going to be y hat. You take x equal to 15, this is going to be y hat, right? Okay, so y hat is what your model is giving you. So let's in fact even look at it very quickly. So here is your y, right? And here is your y hat. Exactly, here is your y hat. So do you see I have two variables? And remember, what is a variable? A variable varies, a variable has non-zero variance, right? So just like y varies and has a variance, so y hat also varies and has a variance, okay? All right, now cut to what is r squared. R squared is telling you, okay, so what extent of variation in y is getting explained by the model. It's just taking the ratio of the variation of y hat to the variation of y. Now, we have like big names for these things, right? So we call the variation in y hat the explained, there are different terms. Sometimes it's called the regression sum of squares. Sometimes it's called the explained sum of squares. There are various terminologies that you can use, all right? But whatever name you call it, it's basically what your model is explaining. It's the variation in y hat, right? So suppose I have a beautiful model, it's wonderful. Then what shall we find? We shall find that most of the variation in y is explained by y hat. So that when I take the ratio of the variance of y hat to the variance of y, I'm going to find something crazy like 90%, 80% and all that, right? But in this case, what do I find? Well, my situation is not very happy. I find that only about 16.5% of the variation in y is actually explained by y hat. Okay, so that's not very great, but then that's what it is, and I'm not very disappointed because I know this is not a good model. I know that, when you're trying to explain variation in wages, variation in education is not the only thing. There are many other things like experience, whether you're a woman, what kind of a job you're doing, are you a clerical worker, are you an officer? All of those things have a bearing on how much of, on what is it that determines how wages vary with education. Okay, so understandably in this model, our R squared, which is a measure of goodness of fit, is not too high. So don't worry about it, but it is giving you a verdict on the model. Now, what I want you to see is the following. Do you see here that there is a analysis of variance table reported right here? What this is giving you, among other things, are the sums of squares. Now, you see, every profession has terminologies. Here also, when you're a researcher, you're using stats, you're using tricks, sums of squares. Instead of saying variance, if you say variance, everyone will understand what you're talking about. So call it a sum of squares, right? Sounds fancy. So variances can also be called sums of squares. That's essentially what they are. Recall the basic formula of a variance, right? Xi minus x bar whole squared and then summed across all the x's. So that's where the sum of squares a bit is coming from, right? Now, what is it giving you? What is this table giving you? This is giving you the regression sum of squares. This is nothing but the variance of y hat. And then it's giving you the residual sum of squares. We'll come to what that is. So right now, I'm not going to worry about the residual sum of squares. So the regression sum of squares and the total sum of squares. So the total sum of squares is nothing but the total variance of y. Ouch, I have a power cut. No, I don't. No, I don't have a power cut. Okay. So, the total sum of squares is the total variation in y, and the regression sum of squares is the variance in y, is the total variation in y hat, or the variance of y hat. And look what you get. So look what I have done over here. I have just divided one by the other. So just look at this bit here, all right, which I have just circled. So here, if you look at the formula, I have just divided the regression sum of squares by the total sum of squares. So C12 by C14, right? And that's exactly, so you should see, that's exactly what the R squared is, all right? Okay. Now, so the R squared is this and a little more, right? What more is there to the R squared? Let's quickly have a look. So I will now switch to my slideshow. Yeah. So, R squared, which is also called your goodness of fit, is basically a way of thinking how well our sample regression line fits the data. That's where this name comes from, goodness of fit. And it's essentially the fraction of the total sum of squares, or SST, total sum of squares, as we just saw, that is explained by the model. Now, what the model is giving you is y hat. So it's basically the ratio of the variance of y hat to the total variance in y, okay? And if you were to just scroll down, sorry, yeah. Yeah, so yeah, right. I just yeah. So there you go. Here you can think about the terminology. The most important part of the terminology that we're going to use to understand what the R squared is to really start with this. Okay, so each observation, so each Y actually has two parts, right? There is a path that's predicted by the model, and then there is the part which is not predicted by the model. So where is this coming from? Remember what we said. We said that the least squares residuals are nothing but y minus y hat, right? So another way of turning that around and saying it is the following, that y, which is the actual observation, is nothing but y hat. So I'm just taking this to the other side, plus the residuals. Now the residuals, I can just call it the residuals, or I can call it u hat. So u is the errors, the residuals which estimate the errors are u hat, okay? So this is exactly what you start by looking at, and then you define the total sum of squares, which is the total variance of y, the explained sum of squares, which is the variance of y hat. Now, you see, it is a thing about your regression model. I'll just run you through those. But the regression line passes through the sample mean. So the regression line passes through x bar and y bar. So you will see that the mean of y is y bar, the mean of wages is y bar, the mean of predicted wages is also y bar. So the mean of y hat is also y bar. So the explained sum of squares, which is the variance of y hat, is also y hat minus y bar whole square. And this is the residual sum of squares. Okay, so you can show following from this. So hang on, let me just. So following from this bit, you can actually show that the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. Okay, because every observation can be expressed as a sum of the predicted values and the residuals. Now, going on from there, you can actually prove this, and that is simple enough, available in any textbooks. I'm not really going through that. So going on from there, you can actually talk about the R squared, which is equal to um, um, either you can talk about it as in this way. So explain sum of squares upon total sum of squares. That is what I showed you in the Excel file. I have just taken these two values from the ANOVA table, and I've showed you that that's exactly what the R squared is. Now that you know what the residual sum of squares is and the relation between residual predicted values and actual, you should check when you are doing this exercise. Please check this. So the ANOVA table also gives you the residual sum of squares, which is the residual variance. Let me just pause here and tell you one more thing. You see, most things in life are actually quite simple. One of the simple things in life is, if you have a variable, the variable is not a constant. So the variable takes different values. If it does not take different values, it's not a variable, it is a constant. So number one, if you have a variable, it will vary. Okay. Number two, when a variable is a true variable, that is, it varies, it will have a variance. Another simple fact of life. Okay. All right. Now, just think about my Excel sheet. How many variables did I have? I had y, dependent variable, x, explanatory variable, prediction, y hat, another variable, u hat, another variable. So all these variables, of course, they will vary, and of course, they are variances, right? So I hope you understand what the residual variance is. It is nothing but the variance of my residuals. Now, uh, again, because of the least squares methodology, you can actually check that the residuals have zero mean. Why do they have zero mean? Very simple. You see, what the least squares method does is, it minimizes the sum of squared residuals, right? What is the least squares line minimizing? It is minimizing y minus alpha minus beta xi, right? So when you are minimizing a sum of squares, you can't drive it to zero because it's a sum of squares. It has to be positive. Where is the natural minimum? The natural minimum is zero, right? So the least squares method is actually minimizing the sum of squared residuals. In the process, always, whenever you have a model which has a constant term, always the residuals will be mean zero. Okay, this is just coming out of the least squares methodology. All right, you have mean zero residuals. Okay, now if the mean of the residuals is zero, what will its variance be? Think about the formula of the variance. Xi minus x bar whole square. Now x bar is 0. So in this case, u hat minus u bar whole square. U bar is the, u hat bar is the mean of the residuals. If the residuals have mean 0, what will the variance be? The variance will not be nothing but the sum of squared residuals. Okay, you can check this. So I repeat. Take a data set, run a regression in Excel, check that Excel is reporting residuals. You make sure you can calculate the same residuals using alpha hat and beta hat and the value of y, okay? And then check that the residual variance, which is reported as part of your ANOVA table, is just nothing but sum of squares of the residuals. So you have to take the residuals, you have to square them, you have to add them, right? And you will get the residual variance. Now, once you've got the residual variance, check that the R squared is nothing but 1 minus the sum of squared residuals, okay, upon the total sum of squares. Okay. All right. Now, There's a little more to the R squared than what you have just discussed. So of course, it's the goodness of fit. It is also square of the correlation between y and y hat. Always. Check this. So generate y. I mean, of course, you have y is your data. Now you have generated y hat, right? I have done this in the Excel file. I'll just show it to you in a bit. So you have y hat. Take the correlation, square it. You will get r squared. All right. So this is true in every case, whether it's a two variable model, whether it's a multiple regression model, always. Okay. All right. Okay. Now, in the two variable model, you have a special result. The r squared is also the square of the correlation between x and y. So yesterday somebody was asking about, correlation and regression and all that. So especially for that person, this is something to note. All right. There's a feature of correlation which is actually sitting right there inside your regression model. So the model R squared is nothing but the squared correlation between y and x. But remember, this is only in the two variable regression model. Generally, the R squared is always the correlation between y and y hat. So since I've done this, let me just show you, and I encourage you to take some data, use Excel, and also check these out for yourself. So note the R squared value, it's 0.16476, and 0.16476 is exactly what you will get when you put the regression sum of squares in the numerator and the total sum of squares in the denominator. That's exactly what is going to give you this. Not only that, look at what I have done here. I have taken the correlation. So you see, what is this, the correlation between? You know, it's getting highlighted it's getting highlighted in Excel. So, okay, all right. Right. So once I take the correlation between wages, which is y, and y hat, right? What do I get? I get exactly 0.16746. All right. So this thing that I have that I've now highlighted in yellow is showing you that when you take the correlation between the predicted values and the original dependent variable y and y hat, all right, you get 0.16476. Now, look at what I have done right over here. Here, I'm going to highlight this in blue, all right? Here, I have taken the correlation between x and y, and I squared it. So that's the other thing, huh? I've squared these correlations. These are not just correlations, they're squared correlations, okay? So when you take so in blue, when you take the correlation between x and y and you square it, you get exactly the model R squared. Why? Because this is a two variable model. So check this, okay? Check these little things about your R squared. Having said all this, you see, don't let the R squared rule you, okay? What do I mean by that? You see, this is something I've seen with many researchers. They get so depressed and so happy, you know, high R squared, happy, low R squared, and you know, you're depressed. Please don't do that, okay? Do not tie yourself, your happiness, your research to the quality of your R squared, to the value of your R squared. R squared is telling you something important, but then remember my 1, 2, and 3. So R squared is just one of them. So let me get back to my results. When I see how good or how bad my results are, R squared is by no means the only thing that you have to worry about. So do not tie your happiness to it, okay? And it cuts both ways. It cuts both ways. So just as a low R squared should not depress you, do not feel so happy just because you have a high R squared, okay? You can still have a rotten model, believe me, with a high R squared, okay? So the message, like, R squared is not my enemy. All right, nor am I trying to build any kind of ill feeling in your heart about the R square. No, but I'm trying to tell you that R square is not the be all and the end all. Okay, so R square is telling you how much of the variance in Y is getting explained by the variance in Y hat. There is more to it, and very, very important is the sign and the magnitude of your coefficients. Are your coefficients the expected sign? In this case, it is, right? I expect that I expect a wage to increase with education. That's exactly what I have. I see that I have a positive sign of my coefficient, indicating that the regression line has a positive slope, which indeed it does. As you can see, it's going upwards. My regression line is actually sloping upwards. Okay, when I scroll up, right? So that is one of the things that you have to worry about. So the sign and the significance of your, so the sign and the magnitude of your coefficients and the statistical significance. So that is what I'm going to come to now. Okay. And as I said that we cannot come to statistical significance until and unless you see, look at what's between standard error. Okay. So the road to statistical significance lies through the standard error. All right. So you'll have to understand what the standard error is. And we've been talking about variables, variances. So let me tell you right up front, what is a standard error? It's nothing but a kind of standard deviation. Why is it a kind of standard deviation? First of all, what is a standard deviation? Whenever you have a variance, you take its positive square root, you get a standard deviation, right? So a standard deviation is the positive square root of a variance, number one. So what is a standard error? Okay, suppose you don't have a variance, but you have an estimated variance. There is a difference, right? Now, where is this difference coming from? You see, the difference is coming from the error term. By the way, let me tell you, if least squares regression is a movie, the hero is the error term. The error term is the Bachchan of Amitabh Bachchan of least squares regression. Everything begins and ends with the error term, right? So you see, remember I told you yesterday, we can't see the errors. The errors are unobservable random variables. Having said that, what did we do? We made a whole bunch of assumptions about the errors, right? We said so many things about the errors. Why? Because we can't see them. So we are assuming that they are mean zero. We are assuming that all the errors are independent, right? We are assuming that they are homoscedastic. Let's come to that. What was that? That was the errors have constant variance. So that means two things. That means whether you take error number 1, error number 2, error number 3, they all have the same variances. The second thing is that as I keep changing x, the error variance does not vary. So whether you are looking at people with 5 years of education, 10 years of education, 20 years of education, right? No matter what x value you take, the distribution of errors, right, has the same variance across all these x values. So the error variance is a constant, which is to say that the error variance is the same across all the errors, and the error variance does not vary with the x's. We had assumed this, right? Yesterday we had assumed this, and we are still assuming this. Okay, so if you can't see the errors, how can you see the error variance, right? That is where the story of an estimated variance enters. Okay. So therefore, my error variance, which I'm calling sigma square, is also unseen, right? Variable ही नहीं देखा, तो variable का variance भी नहीं देखा, right? So you haven't seen the variable, nor have you seen its variance. It is unknown. Now, whenever something is unknown, you estimate it. So we estimate the error variance. How do we estimate the error variance? Can you guess? Okay. Uh, I'll give you. I'll tell you. I'll tell you. It's tea time, so I won't make you guess. I'll just tell you. So you see, errors are being approximated by the residuals. So the error variance will be approximated by the residual variance, right? Now the residuals having zero mean, the residual variance is nothing but the sum of squared residuals. There you have it. The sum of squared residuals are basically used to estimate the error variance. Now here we have a very simple rule. If you are an unknown, you are without a hat, right? Alpha, beta, these are all unknowns. But alpha hat, beta hat, right? Those are estimators, right? Those are equations. And the values of those equations for a particular data set are the estimates, right? Okay. So sigma square is the unknown error variance, hatless. Okay, sigma square is a number I do not know, I do not observe, because I do not observe the errors. So I will estimate it, sigma hat square. So sigma hat is the error standard deviation. Sorry, sigma is the error standard deviation, sigma square is the error variance. Sigma hat square is the estimated is the residual variance which is used to estimate the error variance, and sigma hat is the standard error. Okay, not the standard deviation but the standard error. Sigma is the standard deviation, sigma hat, which is an estimate, is the standard error. And you know, it is so important that it is actually also estimated. So I'll just quickly show you that here you go. Okay, so I'm going to highlight this in like red. Okay, yeah. So what you see highlighted in red over here is the standard error of your regression. Okay, so very important, very important. um, okay. It's so important that there should be fanfare, like, okay, the standard error has entered, because you see it is the standard error of the regression which I have highlighted in red, which will help us get standard errors of our variables, sorry, of our estimators, and those in turn will lead us to the t-statistics, and with the t-statistics we will be able to do hypothesis tests of all sorts. All sorts of hypothesis tests we can do with the standard errors, and we are going to talk about this right after the break. So right now I will break. I think this is the time when I'm supposed to break, and you can just tell me if there are any questions that need to be answered right now, or you know, what should we do? Right. So are there any questions that I should take now? Let me look at the, okay. Can regression number and number of data. So Ashok has a question asking what are the residuals? Ashok, first of all, am I audible? Can someone just confirm, am I audible? Hi. Okay, so Rachita, you're saying I'm audible, right? Can you just say yes again if you can hear me? Dr. Rachita Sharma, can you hear me, all of you? Just say yes on the chat box. Oops. Okay, thank you, Rachita. All right. So I'll just take some of the questions. I'll just go up as I scroll. Okay. So Rajni, you are asking what is the difference between beta and beta hat. Rajni, there's a very important difference. So let me just show you one moment. Okay. So um, uh, okay. So Rajni. Uh, all right. So I hope Rajni that you can see my screen. Um, you see, this is beta. What is beta? It is an unobservable constant. What is it a part of? It is part of my basic theoretical model. I'm saying that there is a straight line relation between y and x. I don't know what that straight line is. I will estimate it using some data on y and using some data on x. So when I'm starting out, I'm specifying my model and I'm saying that y is equal to alpha plus beta. Beta is the slope coefficient. Beta is, as I said, an unobservable constant. That is what beta is. Right. Now cut to beta hat. What is beta hat? To see what is beta hat, let me take you to my notes, which is saying that, look, once you've used the method of least squares, you get a formula for estimating beta. So we estimate beta. So once I have data on x and I have data on y, I estimate beta using this particular formula, which is the covariance of x and y on the numerator and the variance of x on the denominator. This is beta hat. So you see, I'm glad you asked this question because beta hat is many things, right? Beta hat is this equation. Beta hat is your OLS estimator, right? And beta hat is a variable. Okay. Why is beta hat a variable? Because you see, beta hat is a function of x. It's a function of y. What are x and y? X and y are variables. So beta hat is a random variable. It is a very special kind of a variable. It is a function of random variables. X and y are random variables. So beta hat is also a random variable. How do I know that? You see, if I were to change my data set, if I were to change x and y, you bet your life you're going to get another beta hat. Using the same equation, so using the same formula, which is covariance upon variance. So using the same equation for beta hat, you will get a different value. You will get a different estimate for beta hat the minute you change your data, showing you that beta hat is actually a random variable. It is a function of your data. It is a function of the x and y. I hope the difference between beta hat and beta is clear. I will just show you one more thing, which is, you see these numbers here. These are estimates. For this particular data set, 0.54, your beta hat is the estimate. Using the estimator, for this data, I got the estimate that beta hat is 0.54. So you see, there are many things about beta hat, and beta is just an unknown constant. That's it. There's nothing more to beta than it's being an unknown constant. So I hope, Rajni, that is clear. Okay. So now let me take some more questions. Okay. Okay. Right. The minimum value of R squared acceptable, there is no such cutoff. Please explain R squared and standard error. I've already explained R squared, Ritu, and standard error I'll be repeating. So I hope that you will follow. R squared is is nothing but the ratio of the variance of y hat to the variance of y. I will come to T statistics. I will come to how we compute errors. So all of those questions will be attended to later. Will the regression provide better prediction? Can I use it to forecast COVID cases? Of course you can, provided you have a good model. Okay. I don't understand Dr. Vijayalakshmi's question. With Dr. Vijayalakshmi, we are asking, can regression model be used in 5-point scale data with n number of data points? I'm afraid I don't really understand very clearly what you are asking. Let me think about this, Dr. Vijayalakshmi. I'll come back to you. I think I'm getting what you're asking. I will respond. So I will make a note of the questions that you are asking, and I will respond at the end of my session. Voice is not clear. I'm sorry. I mean, I'm trying to, do my best. The wage and education data set will be shared to you, shared with you, later. So please wait. I will explain the standard error part once more, Saida. And what is the relation between p-value and type 1 error possibly? I will talk about hypothesis tests, okay? Then Rajni, I hope your question about the difference between beta and beta hat is answered. What if intercept is negative? Sonia is asking, if the intercept is negative, is it good or bad? Sonia, the thing is that there is no such good or bad. In fact, regression is a tool. Regression is not going to give you verdicts on what is good and what is bad and so on. Okay? Regression is telling you that based on the data, what is it that the data is telling you? So listen to the data. That's all. So if the intercept is negative, it's just telling you that, look, you have a regression line which cuts the y-axis from below 0. Now, I don't know, Sonia, whether you're a student of economics. Sometimes that makes sense. So in economics, we study a savings function. The savings function has a negative intercept. So you can get a negative intercept if you're estimating a savings function. There's nothing good or bad, okay, like that. Always the interpretation has to be taken in context. Nitushri Burman is asking, what should be the ideal value? There is no ideal value of R squared, absolutely not. And your model to be accepted, you have to look at the package. You will have to look at whether the variables have the correct sign, whether they're statistically significant, and then you see what kind of an R squared you are getting. So absolutely, there is no such thing as an acceptable value of an R squared. I will Ishleen, I will just run over the idea of standard error and residuals, and then we will repeat it once we are back after tea. So, so the standard, so the residuals have, the residuals are a variance, and they are estimating the errors, right? So the residual variance is basically giving you an estimate for the, a way of estimating the error variance. So we call the error variance sigma square, and we use the residual variance to calculate sigma hat square. Okay. How I will discuss the formula after the break. Now, just like the standard deviation is a positive square root of a variance, the standard error is the positive square root of an estimated variance. Okay. So once you have sigma hat square and you take under root of that, then you get the standard error. Okay. Which is a estimate of sigma. What is sigma? Sigma is the standard deviation of your error term, which you cannot see. And standard error is sigma hat. It is a estimate of that unknown standard deviation. Again, as I repeated, Sagar, all these R squared values and what they mean are really irrelevant, just irrelevant. They are telling you what fraction of y is getting explained by y hat, right? That's it. So sometimes when your model is really great, you'll have a fairly high proportion. Now in cross-section regression, if you have like 50%, even that is great. Okay. Now sometimes when you have 90%, that's something to worry about. And if you are using time series data, then high correlation is such high R squared is a sure sign of autocorrelation, right? So there is really R squared by itself is not really that much of a thing to worry about. Regression, Dr. Chandrasekhar is talking about the, I think the total sum and all that. I'll just repeat that here you have y. It has a total variance. Part of the total variance is explained by your model, which is y hat, and the rest of it, which is not explained, are your residuals. That's how it works. What is multiple R? Good question. Multiple R is nothing but the correlation between y and y hat. Okay. So if you take, so remember 0.164 is the squared correlation between y and y hat. Just take under root of that. You will get 0.4059. Okay. It is just telling you what is the extent of correlation between the actual dependent variable and the predicted variables. Ashok is asking what are the residuals. Ashok, I hope by now you're understanding what are the residuals. Dr. Vijayalakshmi, as I said, you know, I'm going to come back to your 5-point scale thing. So, right, I think a lot of it is now answered. Are there any more? Okay. Okay. So Vijay, I think I have repeated standard error and R squared, Vijay. So I hope it is clear. The R squared is the variance of your y hat to the variance of y. It's 1 minus the residual variance upon the total variance. So I'll just show it to you once again, Vijay. So, okay. Right. So, yeah. So this is for Vijay. So, we can either think of the R squared as the explained sum of squares upon the total sum of squares, or we can think of it as 1 minus the residual sum of squares upon the total sum of squares. Okay, that is what the R squared is. And this residual sum of squares is also reported as part of your regression. Where is this coming from? This is coming from the fact that SST, okay, sorry, I'll just go up. So it is coming from the fact that your SST is just equal to SSE plus SSR, right? So because your SST is equal to because the total sum of squares is equal to SSE plus SSR, now look at what you can write. You can therefore replace this SSE over here, all right, as SST minus SSR, right? And once you do that, this is what you get, right? So that is the relation between the residual sum of squares, which is SSR, and the explained sum of squares. All right. So Vijay, I hope that is clear. Okay. Why is it called goodness of fit? Because it's telling you, you know, in what extent. So Shilpi, I'm answering your question. It's telling you to what extent your model fits the data, right? So I'll just go back, Shilpi, to answer your question to my Excel file again. And I'll just tell you why it's called the goodness of fit. Okay. So Shilpi, look at this diagram over here. Okay. What is this showing me? This is showing me the regression line. In yellow, it is showing me the regression lines. If I were to join it, I would get this sort of a line, right? Now, all along the line, so all the values of y that I'm going to get along this line are the y hats, right? And what is R squared? The R squared is telling you to what extent the variation in y is being explained by variation in y hat. So do you see? These are your y hats. And what are these blue things? These are your y's. So do you see, to some extent, to where this goodness of fit is coming from, right? It is telling you to what extent is your line fitting the data, right? How many data points is it actually covering? Is it really covering the data points very well? As you see in this case, our R squared is just 16%, and that shows up in the line. The line is kind of really a very sort of a line with a very low slope. Whereas look at the education values, right? They're way higher. So, for instance, if I were to look at some value, let's say 17 or something, people with 17 years of education, my model is saying that on average, they are going to earn about, they are going to earn this much, right? They're going to earn about less than $10 as wages. I'll just repeat that. So let us take someone with about 17 years of education, as I'm doing on my screen. What does my regression predict? It predicts that average wage of such a person is going to be less than $10. But in reality, what do I see? My, look at this. In reality, I see that they earn, and these are hourly wages, right? They earn as much as, well, more than $25. There are lots and lots earning more than $10. So it's telling you that this line is not fitting your data all that well. And that reflects in the 16% R squared. So I hope that kind of answers your question, that what is the relation between R squared and why it is called the goodness of fit. Okay, right. Shilpi, yeah, I hope that answered. Can the significance of R squared be known from the F statistic? I don't know what kind of a question that is. The F statistic and the R squared, Preeti, are related, and both of them are right there. So why do you want to kind of talk about significance and so on? I see, okay, Preeti, sorry, I see where your question is coming from. So what you're pointing to is the fact that the F statistic, which we have not discussed so far in the course, can actually be expressed in terms of a certain R squared and so on. But I just keep them separate, right? The F statistic is also telling us something about the regression, just as the R squared is. I'll come to interpretation of the F statistic, and I don't think we have a lot to say about the relation between the two. Okay, right. So, how can I remove U3? It's not easy to remove multiple linearity. Mostly you have to live with it. Chandan is saying, please explain type 1, type 2 error. I'm not sure what you mean by type 3 error, Chandan. I'll talk about it when I'm coming to hypothesis test. Udvir, of course, we can use multiple regression in panel data. So that is that you will see when you're doing panel data. Archita, do you want me to explain multiple R again? Multiple R is nothing but the correlation between Y and Y hat. You have a model, you have the data, you have Y. Now you just pick up Y hat, you look at the correlation between the two, and there you are, you get multiple R. Okay. Now, since R squared is the squared correlation between Y and Y hat, under root of the R squared should also give you the multiple R. How errors are computed? Somebody who's anonymous is asking. Errors cannot be computed. Okay, errors are unobserved. Okay, you cannot compute the errors. You can only compute the residuals, right? The residuals can be computed as the difference between your your dependent variable and the predicted values, y minus y hat. Okay, all right. So shall we just end this session right now and come back after tea? Is someone from Ramanujan College there? Will kindly respond? Oops. Yeah, sure. R squared and standardized R. I'm not sure what is standardized R. Someone who's anonymous is asking this. I'm sorry, I can't answer that question. Yeah, certainly, Rachita. There are two books that I would like to suggest. Uh, one is this book by Woolrich. So it's called An Introduction to Econometrics, J.W. Woolrich. Okay, I think I have the reference written. I'll just see if I do, I'll show it to you. So one is this book by Woolrich, and the other one is this book by Daugherty. Here. Okay, so this is the book by Woolrich that I think is one of the best books available on the topic. All right, Introductory Econometrics, a Modern Approach, and a book which has a very similar title is a book by Daugherty, Dougherty. Okay, Christopher Daugherty, and if you're an advanced student, then for you a book with advanced topics as well as data commands is this one, a book by Cameron and Trivedi. Cameron, Cameron, okay, I don't know the full name. So Cameron and Praveen Trivedi. It's called Microeconometrics Using Stata. This is an excellent book, but it's an advanced text. So for those of you who are looking to just start off, I would suggest Woolrich or Daugherty, Dougherty. For those of you who have a lot of knowledge and would like to take it further, I would suggest Cameron and Trivedi. The plus point about Cameron and Trivedi is also it tells you all the commands in Stata for the programs that are handled. Okay. Right. So I think, yeah. So Radha, we will after the break we will discuss the standard error of the intercept and the slope. So right now, shall we break for tea? I mean, I think the Ramanujan College had told me that we break at 11, but now it's 11:30 almost. So I will leave the session now and I will come back at 12 o'clock. Any more questions? You know, there's still a few minutes left. Any more questions? So Rachita had suggested some books for Shraddha is asking 1 dB, 2 plus dB. Sorry, Shraddha, I don't understand your question. Is it only used when we have 1 dB and 2 plus dB? Sorry. Shraddha, I'm not understanding your question. Ma'am, we can use in parametric test only. Sorry, Shraddha, I'm sorry, but I really don't understand what you're asking. If you're asking about hypothesis tests in the OLS frameworks, they are very, very parametric tests. These are not non-parametric tests. So we will assume that in the OLS framework, the errors are normally distributed, right? So normally distributed errors basically mean that all the hypothesis tests are based on the assumption of normal distribution. So the T statistics are all normally distributed. So they are certainly parametric tests, okay? And this DV, I just don't understand what you're asking, okay? Standard error, rather, as I said, we will come back to. Sharanya is asking, in multiple regression analysis, can we, of course, yes, yes. In multiple regression analysis, you have many explanatory variables and one dependent. Oh, okay, yes, okay. Shraddha, I get it. So DV is dependent variable, all right. Y and X is easier. Just say Y for dependent and X for explanatory. Okay. 1 dB, 2 dB. All right. Okay. So Shraddha, basically you are asking, so Shraddha, when we have a multiple regression model, we have one dependent variable, we have many independent or explanatory variables. Okay. But what about Y hat? We will only have one Y hat. And multiple R will give you the correlation between that one Y hat and the one Y. even in multiple regression model. Okay? I don't know if that answers your question. Which one is beneficial? Appropriate between R squared and adjusted R squared. Tina, when we are talking about multiple regression model, always adjusted R squared. Okay? So we will always use the adjusted R squared when we are using multiple regression. Okay? Okay. So, okay, so that's it. Fine. So, I will be back at 12 o'clock, folks. All right.
Yes, yes,
So,
ma'am. If it is okay, then we can stop this session here and we start at 12 o'clock again,
12
actually.
o'clock. Yes.
Huh.
Okay, Anjali. Thank you.